Hello. Hello, everyone. So today I'm going to present the work done at King's College in collaboration with Sara Bernardini, Maria Fox, and Derek Long. And I'll talk about our way to tackle problems with semantic attachment. So first of all, I would like to start with an illustrative example that I'll use throughout the presentation to explain some of the concepts that I will present. So this is the hydraulic blocks work introduced by Vankovic in 2014. It's a variation of the blocks work domain where blocks are in a system where there is a vessel with a fluid and some cylinders with some pistons. So the blocks are on top of these pistons, and basically what happens when we pick up a block is that there are some physical equations, and basically the pressure of the fluid has to balance, and therefore the height of the columns of fluid changes. So the problem is how we can formulate and we can solve the this kind of domain in PDDL, in planning and in PDDL. So when we want to express numeric effects in PDDL, what we can do is, for example, increase a variable for a certain quantity, or we can assign a variable to an expression. And in PDDL, in particular, we use algebraic expressions, algebraic expression of numeric variables. But in this case, we can't really express the system of equation that I showed before. We need something else, and in particular we use semantic attachments. So semantic attachments were introduced back in 1980, and they are basically an interpretation of predicate symbols calculated by using external procedure. So we will use semantic attachments to express these complex numeric effects, and the question that we want to answer in this talk is how we can effectively guide the search when we have these kind of semantic attachments. So first of all, a bit of formalism. As I showed in the previous, in our hydraulics blocks work, we can recognize two types of effects on variables. So there are direct effects that are the consequence of applying an action. And for example, in our hydraulics block work was the change in the weight on of the cylinder of our system, but this triggers a sort of an indirect effects. For example, in the hydraulics blocks where this was the change in the height of the column caused by the physical equation of our system. So in our framework, we call semantic attachment a function between a subset of variables in our domain that maps another disjoint subset of variables that we call indirect effect. So basically there are three types of variables, what we call indirect variables that are calculated by these semantic attachments, and then the standard variables, which are divided into standard variables, indirect effects, direct effects, that basically are the variables that once are changed, they trigger these semantic attachments, while the variables that don't have any impact on semantic attachments are called free variables. And this is the example in our hydraulics blocks work. Here we can see the classification of the variables, and this is basically a direct effect. So once, for example, we pick up a block, the weight on the column of water changes by the weight of the block that we picked up, but the effect on the height of the fluid is modeled with this semantic attachment. Okay, so in order to solve problems with this semantic attachment, what we do is to couple a planner with external procedure that calculates this semantic attachment. So in our implementation, we use the planner POPF-TIFF, that is a partial order for search temporal planner built on top of POPF. And basically, we couple this planner with a specialized advisor. And during the state progression, whenever we make a change in at least one of the direct variables, we call the external advisor that in turn calculates the indirect variables that are passed back to the planner. So now we want to basically take some information from the specialized advisor that we can exploit in the heuristic evaluation. So what we can do is basically approximate the effects on the indirect variables. And the simplest effect that we can think of is basically a linear approximation on the effect. And we consider different approximations. So we start from a very simple approximation where basically all the actions have a uniform constant increase or decrease on the indirect variables. And this obviously is not very realistic, but we consider only for comparison, basically. Then the second approximation that we consider is similar to the first one, but in this case we distinguish between positive and negative increases. Then we can also compute different constant based on what we expect that the semantic attachment would be from the initial state. And as last and more accurate approximation, we basically calculate this approximation in every state that we evaluate. And obviously there is a trade-off between accuracy and time that we need to compute these approximations. So in order to test our system, we take 4 different domains, and whenever it's possible, we compare our system with other systems. So for example, for the Earth observation domain, we compare with the planner TFDM, and for the hydraulic blocks world, we compare again with TFDM and another optimal planner. But for 2 of our domains, we can't actually use any other planner because basically these 2 domains have a temporal structure and temporal constraints that cannot be expressed, that cannot be solved with the other 2 planners. So for the first domain, the Earth observation domain that was proposed by Aldinger and Lohr in 2013, we have basically a satellite, and we want to maximize the number of observations that we can do on the Earth. But this satellite has to maintain some constraint on the torque and the zero visibility due to the kinematic of the satellite. So the original paper proposed a model with semantic attachment based on the PDLM language, where basically they distinguish different kind of external modules. But it turns out that we can express the same model within our framework, and therefore we can compare the two approaches, basically. So in this table, we show the time to find the best quality solution for the two planners, and we can see that basically the two planners are comparable. For the second domain, the hydraulics block work domain, we compare again with TFDM and with the planner described in the Ivankovic paper. So that planner, however, was built to model problems with global constraints over primary variables that this morning Sylvie described. But the main difference between one of the key differences between this latest planner and the other two is that this is actually an optimal planner. So we can't really compare solution time. Instead, we compare solution qualities, and we can see that even though our planner and TFDM are not optimal planners, we can compute basically solution very close to the optimal solution. Then we take a second variation, a variation of this problem, where we also had condition on the indirect variables. And we use TFDM and our planner with two different approximations. So we take the basic approximation and the static approximation of the indirect variables that we compute in the initial state. And we can see that TFDM can solve only 11 of the 80 problems that we have, while even the basic approximation, our planner with the basic approximation can solve 70 problems, 60 problems, sorry. But of course, if we use a more accurate approximation, we can actually solve 11 more problems. The main difference between the two settings, the two kind of approximation, however, is in the solution quality. So for the plans computed by our planner, the average plan length is 50 for the uninformative approximation, while it's 20 for the more accurate approximation. The third domain that we consider is the voltage control problem, where basically we have an electrical network and we want to maintain the voltage of the elements of the network within given bounds, and these are the power flow equations that we need to calculate with the external solver. And we consider, in this case, the basically uniform effects with the distinction between increases and decreases, and again the approximation based on linear approximation calculated in the initial state. So in this case, we also compute plans basically without external advisor. What happened is that basically the plans calculated without using the external solver are mostly invalid here. And well, obviously when we have this external advisor, we also always produce valid plans, and again we have that using a more informative approximation results in a better coverage. The last domain that we consider it comes from the search and track problem, where we want to maximize the number of search patterns that an observer has to execute in order to maximize the probability of finding a target. So these probabilities are calculated in this way, and these are basically what we calculate using the external advisor with the semantic attachments. And again, we compare a scenario where we don't use any external advisor. In this case, since the semantic attachments are used only to calculate the metric function, we don't actually produce, we can't produce invalid plans, but of course, the quality of the solution of the plans calculated without the external advisor are poor. And in this plot here, we can find the expected probability to find the target as function of the time of execution of a search pattern for basically all the problem instances that we have, and we can see that not using an external solver impacts the quality of the solution. And in this case, again, also in this case, we find that increasing the having a more accurate approximation have a benefit on the quality of the solution. So this is the average case, and we can see that it has a very more impactful consequence in some of the instances that we solve. And this is basically conclude our evaluation, and these are just some of the remarks. We presented an alternative formalism for semantic attachments, and we presented a planner that supports our formalism for semantic attachments. We showed the impact of approximation that we use to calculate the heuristic value in our planner, and we show that basically having a more accurate heuristic has a benefit both in terms of coverage of the problem solved and in terms of solution quality. And that's it.
We have about 2 minutes for questions. We can take a couple of questions, and the next speaker wants to set up. Get ready. Any questions?
Yeah?
Yeah.
So can you think of other interesting cases where you can get kind of automatic external advisors from the problem formulation or something like that? Other than the linear?
Well, and we can, for example, if we have a function that is bounded, we can always take the maximum and the minimum value of this function, or we can, so in our case, we have only approximations that are increases or decreases. We can also have a little bit more information taking, for example, linear assignation. And I mean, depending on the problem, I guess we can embed some more or less informative.
Any questions? Maybe a lighter question. Are you motivated to try some new domains after the talk this morning?
Of course.
Okay, thank you.